Learning objectives. In this chapter, the user would learn the following in detail: GSM architecture and operations, radio interfaces of GSM, handover, security, general packet radio service, CDMA systems, WCDMA, IMT 2000, UMTS. Code division multiple access. A multiplexing method in which a large set of frequencies are used by wireless stations. A code of n greater than 50 bits is used when using the frequencies. Use distinctive spreading codes to spread the symbols before transmission. At receiving end, a correlator is used to despread the original signal. CDMA codes are sequences of zeros and ones. Sequences are produced from the codes as per the symbols at rates much higher than those of the symbols. Original data transfer rates are called symbols or seconds. Code chipping rates are called chip rates. CDMA codes enable unique identification of signals from different sources and allow different signals to be transmitted through same space, time and frequency slots without interference. First CDMA standard, IS-95, Interim Standard 95, defined by Qualcomm USA. Features of CDMA systems. CDMA system uses spread spectrum. Spread spectrum consists of a large set of equally spaced carrier frequencies FC0, FC0 plus FS, FC0 plus 2FS, FC0 plus n-2fs, FC0 plus n-1fs. Set of n equally spaced frequencies known as chipping frequencies is used for transmission in direct sequence. Signal from each mobile or base transceiver are coded with 4 codes. There are 4 channels used in a user mobile. N-bit code is assigned to each mobile or base transceiver wireless station and each channel of that user. Another M symbol code can also be assigned to each user channel. CDMA systems use a good set of code. All codes are orthogonal to each other and results in autocorrelation at the receiver. CDMA systems give signals of higher voice and data quality and small bit error rate. CDMA systems have soft handover. Soft handover means that an MS at the boundary of 2 adjacent cells does not have to drop calls due to signal break during handover at the boundary region. These provide seamless connectivity to the MS. CDMA systems perform power control by open loop or closed loop methods to solve the problem of drowning of signals from far mobile terminals by those from the near terminals. CDMA more robust for multipath delays and provides higher immunity towards frequency selective fading. IS-95 CDMA1 system. Developed by Qualcomm USA in 1991. Accepted as a standard in 1997. A 2G plus technology. Frequency spectrum 824 to 849 MHz and 869 to 894 MHz with multiple analog channels forming one digital carrier. The standard uses FDD for forward and reverse links as in the case of GSM systems. From BTS to MS forward link. From MS to BTS reverse link. System A services using channels 1 to 311, 689 to 694 and 1013 to 1023. System B services using channels 356 to 644 and 739 to 777. Pseudo noise spreading codes PNQ and PNI with 15-degree generator polynomials GQ and GI. 32767 equal to 215 minus 1 chip sequence generator using the LFSR based circuit used for spreading. 64 channels created and identified by distinct 16-volt codes. Forward linked channels has a bandwidth of 1.25 MHz. output with radio carrier or forward link channel has pilot channel coded with Walsh code W0, synchronizing channel coded with Walsh code W32, paging channels 1 up to 7 coded with Walsh code W1 to W7, traffic channels 55 channels, each with a 0.8 kbps power control message coded with remaining Walsh codes up to W63. Traffic channel processing unit carries voice data, fundamental code channel data, and supplementary data. Combining circuit is used to combine PNQ and PNI baseband channel outputs from total 64 channels. QPSK modulator modulates signals. Properties of forward channel. Frequencies 870.000 MHz plus 0.030i, where I is the channel number. The channel numbers are between channel 1 to 777, where 1 is less than or equal to I, less than or equal to N1. N1 is equal to 777. Channel numbers are between channel number 1013 to 1023, where minus 10 is less than or equal to I, less than or equal to 0. Forward link from base transceiver. BTS short code is decoded, then long code with mask is decoded, and then Walsh code is decoded by BTS to link user in identified channel. Handover. Soft handover. Offset value changes when MS moves from one cell to another. Each BTS adds one of 512 offsets to PN codes. Power control. Open loop control. Only one end, BTS, TR, transmits the signal strength received from the MSR data. The input data of signal strength detected at an end controls the power used by the transmitter. Channel identification. Orthogonal Walsh codes. Modulation. Quadrature and in-phase baseband signals then modulated by QPSK. Carrier identification and synchronization of I and Q pilots. Walsh-coded signal is spread after scrambling of user symbols with long PN codes. The pilots are modulated after the spread with a pseudo-noise code of 15 symbols with two 15-chip period sequences in the I-pilot and Q-pilot channels. QPSK modulator gets inputs from both the channels and then transmits with a bandwidth of 1.25 MHz for each carrier. The efficiency of transmission is equal to 1.2288 MCPS bar 1.25 MHz into 100, which is equal to 0.98 into 100, which is equal to 98%. Traffic channels and multiple user data channels are spread by Walsh codes to enable the distant identification at the receiver. Coded traffic channel data transmitted by PN long code sequencing to synchronize multiple channels and by PN short code sequencing of I and Q pilots to synchronize the multiple transmitter carriers. The short code is used to identify the multiple transmitter carriers at the receiver. Pilot channel. Transmitted by the BTS to MS before the data is transmitted. MS transmits the data at reduced power if the pilot is strong and raises the power if the pilot is weak. Provides a reference to all the MSs in a cell. Transmit with all zeros in place of voice data traffic through the in-phase and quadrature spreading units. Uses the Walsh code W0. A circuit consisting of PNI in-phase and PNQ quadrature spreaders, baseband filters, and QPSK modulator. Traffic channel. Processing units used for baseband transmission of traffic channel and power control messages. Uses long code and mask, PNQ, PNI, and Walsh coding units. Long code scrambling is used for identifying a traffic channel. Data transfer rate matching. Two rate sets, RS1 and RS2. RS2 is optional in CDMA1. When a rate set is fast, for example RS2, the puncturing of 2 bits out of every 6 inputs slows the data rate when using an additional puncturing unit. Blocking interleaving, a technique which enables the use of idle time slots in the frames which have a redefined bit or symbol transmission rate in a channel. Block interleaving means that between successive blocks of a data set, another data set block is inserted. Block interleaving helps in sending 2 data sets simultaneously. Processing units in traffic channel and power control messages using long codes and mask, PNQ, PNI and Walsh codes. Paging channel. The paging channel sends the TMSI temporary mobile subscriber ID information about the traffic channel, response of MS access request during call setup, and information about the adjacent cell base station and its PN offsets. 1 or more paging channels can be used. Each paging channel uses a distinct Walsh code. Synchronous channel data. The synchronous channel message is used for synchronization of chip sequences at the MS. Its messages include the system identification SID, network identification NID, system time, PN short sequence offset, and PN long sequence code state. The synchronization channel uses Walsh code W32 and PNQ and PNI pilot channels. After passing through the synchronizing symbol repetition unit, the signal data burst will become 4.8 K symbol by S. After going through a block interleaving, 4.8 K symbol by S coded at a rate of 1.2288 M chips by S. Reverse link channel has a bandwidth of 1.25 MHz. Include fundamental mode traffic channels and access channels for access message transmission. A preamble transmits before each access channel message. The preamble contains the information regarding message bits so that the receiver can decode that information to process the succeeding message bits appropriately. No spreading of symbols with orthogonal codes. The orthogonal codes used only for encoding the waveform. Combining circuit is identical to the forward channels. Combines the PNQ and PNI baseband channel outputs from the 64 reverse traffic and access channels. The OQPSK modulator modulates the signals in reverse link. Properties of reverse link channel. Frequency. Frequency 45 MHz less than the forward link. 825.000 MHz plus 0.030 I, where I is equal to channel number. The channel numbers are 1 less than or equal to I less than or equal to N1, between 1 and 777, where N1 is equal to 777 and our N2 is less than or equal to I, which is less than or equal to N3. Channel numbers where N2 is between -10 and N3 is equal to 0 are called channels 1013 to 1023. Reverse link from MS. User symbols are Walsh coded to specify the channel, then long coded using a mask and scrambled with short code and then modulated. Unique offset with long codes. Modulation. OQPSK in reverse channels. Channels. The access and reverse traffic channels. Reverse link channel. Processing units used. 64 symbol orthogonal spreader links directly to a PN long sequence spreader in case of the access channel. Processing units differ from the forward channel. Reverse channel 64 symbol orthogonal modulation performed directly, not after the PN long M sequence coding, on the user data, voice or access channel data. The user signal waveform mapped with the orthogonal Walsh codes. User signal waveform encoding is to reduce the bit error rates at the receiver. Orthogonal spreading modulation used to identify the user data. The signal also spreads by long pseudo-noise coding for scrambling later with the orthogonal channelization codes, but at the next stage after orthogonal coding modulation. General Packet Radio Service (GPRS), a speed-enhanced data transmission service designed for GSM systems. Speed-enhanced data transmission by packetizing data and simultaneous transmission of packets over different channels. There are two switching modes: circuit switching, packet switching. Circuit switching. A connection first sets up, then the entire data transmits through the path that has been set up during the connection. Packet switching. Packets of data at any given instant can take multiple time slots or channels or paths or routes depending on the idle slots at that instant. Receiver assembles the packet into the original sequence in the data. GPRS is a packet-oriented service for mobile stations' data transmission and their access to the Internet. Uses the unused slots and channels in TDMA mode of a GSM network for packetized transmission from a mobile station. GPRS. Data packets of a single mobile station transmit through a number of time slots. GPRS deploys SGSNS serving GPRS support nodes. SGSN interfaces to BSCs, base station controllers on one hand, and to other SGSNS on the other hand. GPRS also uses GGSN, gateway GPRS support nodes, to interface to the SGSN on one hand and a packet data network like the Internet on the other hand. The BSCs also connect to the MSCs, Mobile Services Switching Centers, as in case of the GSM system. GSM system, a subsystem of a GPRS system. GPRS employs the GSM physical layer, connects mobile stations for voice data transmission. Also connects the mobile stations to the Internet and packet data networks at higher data rates. GPRS system architecture. Figure shows GPRS system architecture. It shows 4 subsystems: RSS, BSS, NSS and GSS, consisting of a number of BSCs, MSCs, SGSNS and GGSNS. GPRS system architecture. An MS having GPRS capability stores a CKSN cipher key sequence number similar to the cipher key stored in SIM in GSM. Also stores a TLLI, temporary logical link identity, similar to TMSI in SIM. NSS consists of number of serving GPRS support nodes: SGSNS, SGSN1, SGSN2 up to SGSNI, and mobile services MSCs, MSC1, MSC2 up to MSCJ. GPRS system creates a GPRS context which is stored in MS and SGSM. Context has information of status of MS, data compression flag, identifiers for the cell, and channel for packet data, routing area information. An EIR, GPRS Equipment Identity Register, stores the equipment data through the SGSN, helps the authentication, operation and maintenance subsystems. Each SGSN and each MSC in the NSS layer connects to a number of BSCs at the RSS layer. The SGSNs use the frame relay protocol for connection to BSCs. GSS, GPRS subsystem, consists of the SGSN and GGSN, provides GPRS connections to the Internet and other PDNs public data networks. GPRS protocol layers. GPRS protocol layers have some layers performing the function of the neighboring layers without having all 7 OSI layers. Some layers similar to the GSM protocol layers are given below. The mobile station has 4 layers: physical, data link, network and application. Session presentation and transport layer issues are taken care of by the lower layers. BSS has just three layers: physical, data link, and network. Transport and session layer functions taken care of by network layer protocols. The SDSN and GGSN has four layers: physical, data link, network, and transport. Presentation layer functions are performed by the lower layers. Given below are the signaling protocols in the layers between the MS and BSS, BSS and SDSN, SDSN and GGSN. Mobile station and base station subsystem signaling protocols. Physical layer between MS and BTS is called radio-like layer in the GSM system and has similar functions. Data link layer protocols between MS and BSS link the physical layer, which has the interface UM. Data link layer at MS has three sublayers: Media Access Control MAC, Radio Link Control RLC, Logical Link Control LLC. Data link layer at BSS has two sublayers: MAC, RLC2. A special LLC provides FEC and ARQ automatic repeat requests. Mobile station and base station subsystem signaling protocols. Network layer at the MS has two sublayers: IP/X.25. Subnetwork Dependent Convergence Protocol SNDCP. These two sublayers are below a network sublayer for the convergence of IP/X.25 network layer above SNDCP and three sublayers at the data link layer. Convergence. Multiple ways of connecting network and data link layers through a common protocol. Here, IP.X.25. IP and X.25 are packet formatting protocols for the transmission and reception of packetized data. There are two services: voice data RLC is used and data only terminal service as an internet MAC LLC IP. SNDCP is the convergence protocol for both services so that both can be delivered through IP/X.25. Application layer at MS provides end-to-end applications like voice and internet. Mobile station and base station subsystem signaling protocols. Figure: protocol layers between the mobile station and BSS. Base station subsystem and serving GPRS subsystem signaling protocols. Physical layer for transmission and reception of data and network information between BSS and SDSN is frame relay FR. FR also implements several functions for data logical link. Data link sublayers at BSS and SDSN transmit and receive using BSS-GP, base station subsystem GPRS protocol. Data link sublayer at SDCN is LLC. Network layer at SDSN transmits and receives using SNDCP. Serving GPRS support node and gateway GPRS support node signaling protocols. Physical layers between SDSN and GGSN are layer 1 L1 protocols of Internet or other PDN, PSTN, ISDN and PSPDN. Data link layer protocols between SDSN and GGSN or layer 2 L2 protocols of Internet or other PDN, PSTN, ISDN and PSPDN. Network layer protocol layers between SDSN and GGSN are IP layer 3 L3 protocols. Two transport layer protocol layers at SDSN are TCP or UDP and GTP, GPRS tunneling protocol. TCP is for X.25 protocol at layer 3 and UDP is for IP protocol at layer 3. GTP uses TCP and IP or UDP and IP. Global system for mobile communications. Most popular mobile communication standard. GSM communication uses cellular networks. GSM, a second-generation 2G communication standard. The GSM standard operates in the frequency ranges of 3 bands, 900, 1800 and 1900 MHz. Tri-band, operable in GSM, 900, 1800, 1900 phones enable easy international roaming in GSM networks. Frequency bands contain a range of frequencies used for downlink and uplink. GSM services. GSM provides integrated services for voice and data, teleservices, supplementary services, bearer services. Integration of teleservices, supplementary services and bearer services in a GSM system. Connection. A mobile station MS has a mobile terminal MT. Mobile terminal acts as an interface between a communication network, example, a GSM public LAN mobile network, and a terminal. Interface is a radio interface, a communication hardware and software which sends radio signals and detects signals. TE is used by a caller to connect and talk to communicate. MT is responsible for mobile communication and TE is the source or destination of the service. An antenna is also used as part of a communication system. A connection is established between two TEs, the source and the destination. The destination TE may or may not belong to a GSM network. Depends on the source, destination network, which may be a GSM, PSTN, Public Switch Telephone Network, ISDN, Integrated Service Digital Network, PSPDN, Public Switched Public Data Network, or any other network carrying the data to the endpoint TE. There are 4 sets of interfaces, 18, 27, 36 and 45 as shown in the figure. Each of the 4 transceivers can transmit as well as receive in full duplex mode. Full duplex mode means simultaneous two-way transmission. The MT interface can also be half duplex transmission. Half duplex means the two-way transmission possible but not both ways at the same time. Example of establishing connection in a GSM network. A GSM mobile phone connects to another GSM phone. In this case, a mobile station TE at the caller end interfaces to a GSM public landline or mobile network. The destination for the call and source for the reply is another mobile station TE which interferes the source destination network, a GSM public LAN mobile network in this case. Teleservices. Teleservices are services offered by a mobile service network to a caller TE. Some of the teleservices provided by GSM service providers are telephonic voice at full data rate 13.4 kbps, fax, SMS, emergency number, international SOS number 112 for emergency calls, MMS supporting GIF, JPG, WBMP, teletext and video text access. GIF, JPG and WBMP are formats of files that store pictures. Point-to-point communication is from one TE to another TE. A point-to-point service is implemented using cellular communication. Additional teleservices are half data rate speech or enhanced full rate speech services, and these may or may not be rendered by cellular and point-to-point access systems. For example, a GSM smartphone which connects to a GSM public LAN mobile network offers a number of teleservices including phone, voice data. Example, recorded message played by an auto answer of incoming calls, SMS an MMS to another GSM or PSTN network. GSM services, teleservices. Supplementary services. A mobile service network also provides supplementary services to the caller and destination TEs. Some examples are caller line forwarding, redirection, caller line identification, line identification to the caller, closed user group formation, multi-party groupings. Example in an enterprise: call holding, call waiting, and barring calls from specified numbers or group. Restricted provisioning of certain services to the users. Internet and email access granted on special request from users. Providing information regarding call charges, remaining phone account balance, etc. GSM services, supplementary services. Bearer services. Responsible for transmission of data, voice signals are also transmitted as data between two user network interfaces using the intermediate interfaces at a mobile network. Bearer means a set of data which is transmitted from or received by a TE, that is, the voice data or data set that has been formatted in certain specified formats. This data transmits at certain standardized rates through the interfaces. Voice data. Data that is obtained after digitizing, coding, encoding, appending error detection and correction bits and encrypting of a voice signal. Each TE has a user interface. The interface of a mobile station connects the MT to a GSM public LAN mobile network. The interface of a PSTN phone connects to a PSTN network. An intermediate PSTN network acts as an interface for a GSM public LAN mobile network. In place of PSTN, there may be ISDN, PSPDN, or some other network. A bearer service can be transparent and uses data rates of 2.4 kbps, 4.8 kbps, or 9.6 kbps. Non-transparent and uses lower data rates 300 bps to 9.6 kbps. Data transfer in bearer services is also classified in three types: synchronous data transfer, asynchronous data transfer, synchronous data packet transfer. GSM services, bearer services. Transparent data transfer means that the interface for the service is using only physical layer protocol. Physical layer is the layer which transmits or receives data after formatting or multiplexing using a wired, wire or fiber, or wireless, radio or microwave medium. The physical layer protocol in a GSM bearer service provides for FEC, forward error correction. Forward error correction, FEC, entails insertion of redundant bits along with the data to be transmitted. Redundant data allows the receiver to detect and correct errors. FEC requires higher bandwidths due to additional bits, advantageous in situations where retransmission is not convenient. Enables broadcast to multiple destinations from a single source. Helps in broadcasting without handshaking through FEC transmission, reduces data rate. Handshaking refers to interchange of acknowledgements between two networks or systems once the connection is established between them. Reduction in data rate with m redundant bits appended in a data stream of n bits. Total number of data bits transmitted from the sender's end, n plus m bits. At the receiving end, an algorithm employed to detect and correct transmission errors. Errors means 0 received as 1 or 1 received as 0. The algorithm extracts the original n bit streams from the received n plus m bit sequences. Therefore, for every n plus m bits sent by the sender, the receiver receives only n bits of actual data. means that if the transmission channel offers a data rate R, then the actual data transmission rate with FEC is R into N divided by N plus M. If M equal to 2N, then transmission is called 1 by 3 FEC. Example for data with FEC transmitted through a channel at the rate of 9.6 kbps. If redundant data inserted is 3 times more than the original data, what will be the rate at which the receiver actually receives the relevant data? Solution: actual data rate is equal to R into N by N plus M. R equal to 9.6 kbps, M equal to 3N. Therefore, actual data rate equal to 9.6 into N by N plus 3N equal to 9.6 by 4 kbps, that is equal to 2.4 kbps. Non-transparent data transfer. Non-transparent means the service interface uses physical layer, data link layer and flow control layer protocols. Data link layer is the layer which frames the data and appends additional bits to ensure very small error rate. Framing refers to combining and appending additional bits and header. Flow control layer controls the flow of data by selecting or rejecting erroneous data transmitted and by retransmitting erroneous data. Protocols for data link and flow control layers provide error detection and correction, selecting, rejecting and retransmitting of data. For example, when data is transmitted at GSM 9.6 kbps, the data error rates are high. This is because when non-transparent data is transmitted at 9.6 kbps, there is no retransmission and erroneous data just gets rejected. Data error rate becomes negligibly small at slow data rates 300 bps. This is because the erroneous data is corrected or gets retransmitted using data link and flow control layers. A special error correction facility called RLP, Radio Link Protocol, used in GSM network is an example of a non-transparent communication protocol. RLP results in more robust transmission with very small BER, bit error rate. Synchronous data transmission. Data transmitted from a transceiver at a fixed rate. Constant phase differences and thus time intervals maintained between successive data bits or frames. Receiver must synchronize the clock rate according to the incoming data bits. Receiver also synchronize data bits coming in from multiple paths or stations and compensate for the varied delays in received signals. Handshaking is not used in synchronous transmission of data. Synchronous data transmission fast. No waiting period during data transfers. Example of synchronous data transfer in a GSM system. Voice and SMS data transfers. Voice is converted into bits after coding in a GSM system and the bits are transferred at data rates of 13 kbps as synchronous data. There are no in-between acknowledgements or waiting periods in this transmission of bits. An SMS is transmitted through a GSM channel or synchronous data. There are no in-between acknowledgements and any transmission errors are corrected using FEC. Asynchronous data transmission. Data transmitted by the transceiver at variable rates and constant time intervals are not maintained between consecutive data sets or frames. There is usually handshaking or acknowledgement of data in asynchronous data transfer. Even if there is no acknowledgement when data flow maintained by using the FEC and buffers, transmission can still be asynchronous. Use of buffers cause variable delays in reception. Examples of acknowledgement of messages: receiver ready, receiver not ready, receiver's acknowledgement for acceptance of data unnumbered, receiver rejection, set asynchronous balance mode, disconnect. Program files containing middleware for mobile devices have to be transmitted by the mobile service while maintaining full data integrity. In file transfer cases, the in-between acknowledgements of transmission of bits and reporting of errors during transmission is important. Non-transparent data flow. An acknowledgement is sent by the receiver for each data set to the effect that the data set received is identical to the one transmitted. Time is therefore spent in implementing appropriate algorithms for data set integrity checks and acknowledgements. This results in asynchronous data transmission. Synchronous packet transmission. Each packet flow is transmitted as synchronous data. There is no handshaking or acknowledgement of data during the flow of packets. Packets flow through different interfaces, routes, channels, or time slots to reach a common destination. Time taken for each packet remains constant after the route path is established. At the destination, various packets are arranged in their original sequence. A sequence number transmitted along with each packet helps in sequential arrangement of packets at the receiver. Each packet flow transmitted as synchronous data. Example: n bits of data are to be transmitted as packet switch data. The data transmission rate is n by t. The time taken to complete the synchronous packet transmission is equal to t divided by n into n is equal to t. Time interval t to transmit n bits. If data transmission formatted into 4 packets A, B, C and D. Assume 3 different routes are available for transmission. Packets A, B and C will be simultaneously transmitted along 3 routes. Last packet D will have n-3n bits. Time taken to transmit D is equal to n-3n divided by n by t. If n is equal to 4n, time taken to transmit D is equal to 4n minus 3n by n by t, that is equal to n by t is equal to t. Total time to transmit A, B, C and D is equal to t plus t is equal to 2t. If the same data was transmitted using a single path, time taken is 4t. GSM network architecture. Subsystems of GSM architecture: radio subsystem RSS, network subsystem NSS, operation subsystem OSS. Radio subsystem of GSM system comprises of all radio-specific entities in GSM network. RSS performs the basic functions of connecting the mobile station to the network. Consists of number of mobile stations MS, base transceiver stations BTS, base station controllers BSC. Mobile station base transceiver station interface Mobile station is the mobile device or phone, connects to the GSM network. MS consists of a mobile terminal MT. MT means the device having hardware and software to transmit and receive GSM data. MS also has user terminal TE through which data is sent and received. Subscriber Identity Module SIM. Each MS has a SIM, a card inserted into the MS, provided by the GSM service provider. Uniquely identifies the user to the service, enables the MS to connect to the GSM network. When the MS connects to the GSM subsystems, The SIM saves a temporary mobile dynamic cipher key for encryption, temporary mobile subscriber identity (TMSI), and location area identification (LAI). Contains a PIN, personal identification number. Using the PIN, the MS is unlocked when it seeks connection to another MS. The user can use the PIN to lock or unlock the MS. Information which does not change when the MS moves into another location. International Mobile Subscriber Identity (IMSI). Card serial number and type. IMSI. SIM stores the International Mobile Subscriber Identity (IMSI), unique 15-digit number allocated to each mobile user. IMSI 3 parts: a 3-digit mobile country code (MCC), a mobile network code (MNC) consisting of 2 digits, and the mobile subscriber identity number (MSIN) with up to 10 digits. Same IMSI all over the globe. Identical coding scheme. Helps service providers in identifying and locating an MS. Helps the MS in obtaining the cipher key, TMSI and LAI from the mobile service provider during connection setup. TMSI used to identify an MS during a connection for protecting the user ID from hackers or eavesdroppers. SIM functions. Stores the PUK, PIN unblocking key, which enables the subscriber to unlock the SIM if it is accidentally locked due to some reason. Stores a 128-bit authentication cipher key provided by the service provider. The MS authenticates by a switching center through an algorithm using this key and a 128-bit random number dynamically sent by authentication center. If the MS is not authenticated, the service to that number is blocked. Radio subsystem base transceiver station BTS interfaces to a number of mobile station MSs. Each MS establishes connection through the user interface UM. UM is the ISDN U interface for mobile. The BTS to MS connection through UM. A BTS is also connected to a BSC through the ABIS interface. ABIS transceiver transmits and receives data with 4 multiplex channels. Transceiver of each channel transfers data at 16 kbps or using single 64 kbps fixed line channel. Using a BTS is used to manage one cell in the GSM cellular network, but using a sectorized antenna, a single BTS can be used to manage many cells. Main functions performed by the BTS. Formation of cells using appropriately directed antenna. Processing of signals. Amplification of signals to acceptable strength so that they can be transmitted without loss of data. Channel coding and decoding. For example, coding voice into bits so that it can be transmitted at 13 kbps and decoding received coded signals back to voice. Frequency hopping so that multiple channels for various mobile stations can operate simultaneously using different channel band frequencies. Encryption and decryption of data. Paging to an MS. Adapting to the rate of data. In synchronous data transmission, the receiver clock of the transceiver at one end of an interface adapts itself according to transmitter clock of the transceiver at the other end. Mobile station to BTS interface in a GSM cell. Radio subsystem, base station controller. Manages a number of BTSs. Uses the ABI's interface to connect to BTSs. BSCs reserve radio frequencies for communication and manage handovers between BTSs. A BSC along with the BTSs connected to it and the mobile stations managed through it forms a base station system BSS. Also connected to an MSC in the networking and switching layer using an interface A as shown in figure. Important functions performed by the BSC. Processing of signals. Controlling signals to the connected BTSs and control of handover of signals from one BTS to another within a BSS. Control and handover of the signals from BSC to MSC. Mapping the signals of a channel at given instant receive signal from a BTS at 16 kbps through ABs and interfaces them to an MSC at 16 kbps. Alternatively, may have to interface to a PSTN switching center at 64 kbps through a fixed line network mapped by assigning a 16 kbps channel for 64 kbps signals and vice versa. Reserving radio frequencies. Frequency hopping. For example, multiple BTSs operate simultaneously by using the different frequencies at a given instant. Traffic control by continuous measurement of the frequency channel spectrum being used at a given instant. Authentication, encryption and decryption of data. Updating location registry for the MSS. Paging. Architecture of RSS. RSS consists of a number of base station controllers BSC, and each BSC connects to a number of base transceiver stations BTS, which in turn provides radio interfaces for mobile devices MT. Various BSCs in RSS layer connect to MSCs in the NSS. A single MSC can connect to multiple BSCs. Each BSC communicates with a number of BTSs and so on. If RSS consists of K BSCs, J BTSs and I mobile station, then I is greater than J is greater than K. A BSS base station layer consists of a set of BTSs interfaced to a BSC. Figure below depicts the various components of the RSS architecture. Network subsystem NSS of GSM system. NSS consists of a number of mobile service switching centers MSCs. Each MSC interfaces to a number of BSCs in the RSS. There are also home location registers HLRS and visitor location registers VLRS. Acts as an interface between wireless and fixed networks. Mainly consists of switches and databases and manages functions such as handovers between BSS, worldwide user localization, maintenance of user accounts and call charges, and management of roaming. Mobile Services Switching Center MSC consists mainly of high-performance digital ISDN switches. Connects to a number of BSCs over the A interface. Connect to other MSCs and to fixed line networks through gateways, MSCs, GMSCs. Gateway is a node connecting two different types of networks, used to manage BSCs in a geographical area. Functions performed by an MSC. Processing of signals, establishing and terminating the connection between various mobile stations via BSCs. The mobile stations to be connected may fall in a given MSC's own area or in the area assigned to another MSC, in which case the communication path has to be via the other MSC. Establishing and terminating the connection between an MS and a fixed line phone via a GMSC or IWF. Monitoring of calls made to and from an MS. Call charging, multi-way calling, call forwarding and other supplementary services. Home location register. Has the MT databases. Stores all the relevant subscriber data including mobile subscriber ISDN number, MSI SDN, details of subscription permissions such as call forwarding, roaming, etc., subscribers ISMI, users location area, users current VLR and MSC status. Each mobile user has only one HLR record worldwide, which is updated and constantly on a real-time basis. Each MS must register at a specific HLR of a specific MSC. The HLR contacts AUC in the OSS for authentication. Each HLR is associated to an MSC so that when an MS registered at a certain HLR moves to another location area LA serviced by another MSC, the user's home MSC update the user's current VLR. HLRs help in location updating of a mobile station. visitor location register at each MSC. Each MSC has a VLR. VLR is a dynamic real-time database that stores both permanent and temporary subscriber data, which is required for communication between the MSs in the coverage area of the MSC associated with that VLR. The VLR is an integral part of the MSC. Gateway Mobile Services Switching Center, GMSC, a special node which handles connections to other fixed networks. These other networks may be ISDN, PSTN, PSPDN, or other PLMN networks. Special IWFs may be used by a GMSC to connect to public data networks such as the X.25. Architecture of NSS. Figure shows the architecture of NSS and the interface between the NSS components and the AUC and the OMC in the OSS. Consists of Mobile Services Switching Centers MSC, M&N Home and Visitor Location Registers, Gateway MSCs, GMSC, and Interworking Functions IWFs with the Mobile Switching Centers. GMSCs and IWFs connect to the other network, for example PSTN, ISDN or PSPDN. Interfaces in the NSS between MSC, BSCs, VLR and OMC. Basic connections and components in the NSS can be summed up as follows. Each MSC in the NSS can manage several base station systems. Every MSC has an HLR and a Visitor Location Register VLR. An MSC can connect to another MSC, GMSC and IWF. An HLR connects to an AUC in the OSS. A GMSC can connect to an OMC in the OSS. GMSCs are also used to connect to a PSTN, ISDN or PSPDN network. Operation Subsystem OSS in GSM system. OSS facilitates the operation of MSCs, administers the operation and maintenance of the entire network. Operation and Maintenance Center OMC monitors and controls all other network entities through the O interface. OMC functions: management of status reports, traffic monitoring, subscriber security management, accounting and billing. Authentication Center AUC, used by the HLR to authenticate a user. The AUC may also be secured partition part of the HLR itself. Since mobile networks are vulnerable to attacks, GSM standard specifies that the algorithms for key generation should be separated out as an OSS network entity. This entity is AUC. AUC databases store subscriber authentication keys. Other task is calculation of authentication parameters and then conveying these to the HLR. The Equipment Identity Register EIR stores the International Mobile Equipment Identity IMEI numbers for the entire network. IMEI enables the MSC in identifying the type of terminal, mobile equipment, manufacturer and model and helps the network in locating the device in case it is stolen or misplaced. EIR contains three types of lists: a black list that includes mobile stations which have been reported stolen or are currently locked due to some reason; a white list which records all MSs that are valid and operating; a grey list including all those MSs that may not be functioning properly. OSS architecture. OSS consists of an AUC Equipment Identity Register EIR and an OMC. Each AUC is associated with an HLR in the NSS. Each EIR connects to an MSC. An OMSC at OSS can connect to an MSC or a GMSC in the NSS and to a BSC at RSS. Interfaces between AUC, HLR, EIR and MSC, OMC, BSC and GMSC. GSM architecture. Interfacing between the three subsystems in a GSM network. Radio interfaces of GSM. Antenna radiates the electromagnetic waves according to the electric signals given to it. Electromagnetic propagates between the transmitter and receiver. Waves generate electric field in the receiver antenna as per the electrical signal sent from the transmitter. A radio interface is transceiver, transmitter and receiver of the signals. interface is a radio interface between the mobile station MS and base transceiver BTS. Interference means one signal modifying the other. The signals of same frequency band cannot access the medium at the same time. SDMA multiplexing. A method in which the same set of frequency components of the same range and at the same time slot can access the medium in different direction or cells. TDMA multiplexing. A method in which frequency components of same range in same direction or cell can access the medium in different time slots for the different radio interfaces. FDMA multiplexing. A method in which different set of frequency components of a frequency range are allotted to different radio interfaces and they can access the medium in same direction or cell and in same time slots. Space division multiple access SDMA. Assume that BTS-PQ with N-directed antenna covers mobile stations in N cells. Each cell defines a space. A given BTS covers the PTH cell and the cell is presently covering K mobile stations MS1, MS2 up to MSK. K can vary with time. MS can always change its location and move into another cell. There is space division multiplexing of the signals from the MSs. Figure shows SDMA from mobile station cell I and cell J using the same radio carrier channel CH and M in the same time slot. Time division multiple access. A set of maximum 8 MSs out of 1 MSs can be assigned a radio carrier channel by a BTS. Assume that cell I is presently covering 8 mobile stations, MS1, MS2 up to MS8. There is time division multiplexing of the signals from each set of 8 MSs. Figure shows TDMA from mobile stations in cell I using same radio carrier channel CHM in different time slots. An MS can use the same radio carrier channel CHM in one or more of the 8 distinct time slots, SL0, SL1 up to SL7, each of 577 µs. Data bus in a data frame. A set of data bits in a SL is known as burst. A set of 8 data bursts defines a data frame. A mobile can send multiple data bursts within a frame. Each frame uses different channel radio carrier frequency. Half-duplet transmission. The transfer of a mobile device can function in half-duplet mode when the uplink time slot is at TU and downlink time slot at TD are assigned separately by a BTS and TU-TD is constant at 577 µs. Example. Consider 3 mobile stations MS1, MS2 and MS3 transmitting in a cell. How will the burst from these MSs be assigned in 8 time slots using same carrier channel CHM? Assume B1 assigned SL0, B2 assigned SL1, SL4 and SL7, B3 assigned SL2 and SL6. Assume B1, B2 and B3 the data bus of MS1, MS2 and MS3 respectively. At an instant, a data frame can have bus B1, B2, B3, X, B2, B3, X, B2 transmitted in 8 time slots SL0 to SL7 respectively. X represents unassigned slots for access by either BTSJ or other MSS that are using the same radio carrier channel. Since an SL is equal to 577 µs, data burst period is equal to 577 µs. Each data frame transmits in 8 into 577 µs is equal to 4.615 ms. Frequency Division Multiple Access FDMA. FDMA transmitter allots the available spectrum bandwidth by dividing into different frequency channels for communication by multiple sources, sets of MTS. Figure shows FDMA by mobile stations in cell I using different radio carrier channels. Frequency Division Multiple Access FDMA. A set of maximum 124 radio carrier channels, each of 200 kHz bandwidth, can be used in GSM 900 downlink channel, MSE to BSE, BSE to BTS and BTS to MS. 124 in the uplink channel, MS to BTS, BTS to BSC and BSC to MSC can be used. Each channel transmits data frames of 4.615 ms, 8 time slots each. The frequency slot for each channel is 200 kHz. A set of maximum 8 MSs out of /MSs can be assigned by BTSJ, a radio carrier channel frequency for uplink. Downlink frequency is greater than uplink frequency of a radio carrier channel by 45 MHz. The 124 frequency slots in GSM 900 in the uplink frequency range, channel 1 890.1 MHz plus or minus 100 kHz, CH2 890.3 MHz plus or minus 100 kHz and so on till CH124 914.9 MHz plus or minus 100 kHz. Downlink frequency slots CH1 935.1 MHz plus or minus 100 kHz, CH2 935.3 MHz plus or minus 100 kHz and the last frequency is CH124 959.9 MHz plus or minus 100 kHz. A GSM system station is permitted use the CH2 to CH123 only. All the BTSs taken together can communicate over 90 channels, CH0 up to CH89 available in GSM band. Total number of reserve channels can be 32 for the data transmission of mobile service provider. Frequency hopping in data frames. Hopping means changing a channel for a set of 8 MSs. A data frame frequency channel assigned to an MS by the BTS can be changed to select frequencies at a certain rate according to a predetermined sequence. This helps in ensuring better signal quality for most of the period. GSM hopping rates are 207.6 HOP/s. Specific frequency values result in signal fading during propagation. Do not provide expected signal strengths at the receiver's end during transmission. Format of a data burst. There can be variable delays during transmission as the reflected signals take different amounts of time. Original signals can be reconstructed using a digital signal processor DSP, but the DSP spends computational time in processing the signals. Total 148 bits are transmitted in a data burst. 114 bits are user data or control data. 6 bits, 3 at the head H and 3 at the tail T, both are called tail bits TB. At H bits at the beginning 000. At T bits at the end 000. 26 bits in the middle of the burst are transmitted as training TR bits. The TR bits enable the receiver to synchronize using H, TR and T bits and select the strong components of the signals. Division among 142 minus 26 bar 2 equal to 58 bits, each after H and before T. Data in the burst can be of two kinds, MS data or mobile service NSS control data. On either side of the TR bits, an S bit can be placed to specify whether the source is the MS or NSS control data. Meaningful data bits are 57 after H and 57 before T. Division among 57 bits, each between H and TR and T. Assuming that only one time slot used in a data frame of 8 slots when transmitting voice, and assuming that the only data bus or voice data bus. Total 114 bits, 57 plus 57, for the user data in a data burst time slot. Traffic multi-frame. Total 26 data frames in one, in which there are 1 control data, 1 empty and 24 user data frames. Traffic multi-frames transmit TCH, FACCH and SACCH data. 12 slots for user data. User data is followed by 1 slot for control data signals. Therefore, only 12 out of 13 data bursts are used due to need for frequency correction and synchronization bursts. The voice data user data rates are 12 by 13 into 24.7 kbps equal to 22.8 kbps. This is when only one time slot is allocated for use in a data frame of 8 slots. Traffic multi-frame transmits in 26 into 4.615 ms equal to 120 ms interval. Has just one data burst for control data out of 26. Data control channel rate is 1 divided by 26 into 24.7 kbps equal to 950 bps. Interleaving in a traffic multi-frame. Interleaving means inserting in between. The packets, each consisting of 456 bits in a 20 ms time slot, are interleaved in a traffic multi-frame for voice traffic. Figure shows interleaving of data from the mobile stations in a traffic multi-frame during 120 ms interval. Example to show how two mobile stations interleave data in the traffic multi-frame. Assume two MSs, MSI and MSJ multiplexed in TDMA slots data bus. There are 57 bits after H and 57 bits before T in the data bus. TCH by F, traffic channel full rate, transmission rate is equal to 22.8 kbps. Therefore, there are 456 equal to 8 into 57 bits per 20 ms in voice traffic from 2 MSs. When 20 ms packets of MSI and MSJ interleave, then all the 57-bit time slots after H in each data burst are used by MSI and all the 57 bits before T in each data burst are used by MSJ. Interleaving distributes the effects of channel characteristics variations with time on multiple MSs. 4 types of control data bursts. Different type of control data bursts are required as follows. Access grant channel AGCH, synchronization channel SCH, frequency correction channel FCCH, dummy burst. Access grant channel AGCH. The call setup takes place when setting the initial connection using a burst called access burst. The channel in which this burst is sent is called AGCH, access grant channel, a part of CCCH, common control channel. Synchronization channel SCH. The TR bits help the receiver in correcting path changes. All the MSs that are communicating with the BTS must be synchronized. The total time durations of forward and return paths vary as some MSs are closer than the others. A timing advance required for synchronization when a BTS receives a signal from a far-off MS compared to a short-distance MS. Synchronization burst is used. SCH synchronization channel. The channel used for this burst, a part of BCCH broadcast control channel. Frequency correction channel FCCH. A deviation in the frequency of a radio carrier may occur. Interference with the neighboring channel frequency is also possible. During synchronous data transmission, the receiver must synchronize the clock rate according to the incoming data bits. Frequency correction burst from the BTS helps in correcting the carrier frequency. In place of TR, S and user data bits, a 142-bit sequence between H and T is deployed. FCCH frequency correction channel. The channel for this burst sent a part of BCCH. Dummy burst. When no useful burst being transmitted from an MS or BTS after the connection setup, then a dummy burst is transmitted. Traffic and control data channels. If the transmitted data is not correctable at the receiver, it's blocked for further processing. Traffic data channels. Voice coding using a codec decoder. A codec circuit codes analog signals into digital signals and decodes digital signals into analog according to various coding and decoding algorithms. The error correction bits, cycle redundancy check CRC, and redundant bits appended and data interleaving is performed. 3 types of voice traffic. Voice at full 13 kbps, half data rate speech, enhanced full rate speech. User data or subscriber data is also called traffic data. Different types of voice traffic. TCH/FS traffic channel / full rate set for transmission. TCH/HS traffic channel / half rate set for transmission. TCH/EFR traffic channel / enhanced full rate set for transmission. TCH/F14.4 traffic channel / full rate at 14.4. TCH/F9.6 traffic channel / half rate at 9.6 kbps. TCH/F4.8 traffic channel / half rate at 4.8 kbps. TCH/FS voice coded with a codec decoder at 13 kbps. Additional bits appended after coding, the data rate is enhanced to 22.8 kbps when transmitting at full speed. TCH/HS coded with a codec at 5.6 kbps, and after the error correction bits, the data rate is enhanced to 11.4 kbps and transmission takes place at half speed. The available data rate is 22.8 kbps. Advantage is that double voice signals can now be transmitted. However, this sort of voice rate results in degradation of voice quality. TCH/EFR coded with another enhanced coding technique employing a codec. EFR gives an enhanced voice quality but has limited error correction bits because the data rate is limited to 12.8 kbps. Advantage is that the voice quality upgraded in those cases where the transmission error rate is small. A codec may function in automatic mode and code the voice as TCH/FS or TCH/EFR depending on the transmission error rate detected in the burst. TCH/F14.4, TCH/F9.6, TCH/F4.8. Due to large number of subscribers at a base station, the GSM specifications provide for the traffic rates of 14.4 kbps, 9.6 kbps and 4.8 kbps also. Control data channels. The 184-bit packet from data link layer is formatted for the data burst bits. The 184 bits are added with 40 parity bits, 4 tail bits and 224 half convolution coding bits. Total result in the 456-bit packet, multiple of 114 bit in a data burst. There are 4 formats for control data burst in data frames. Can also be formatted as 456-bit packet, with different coding procedures than in traffic multi-frame. Various types of control channels: CCH, DCCH, dedicated control channels; BCCH, broadcast control channel; CCCH, common control channel; DCCH, dedicated control channels. An MS sends TCH traffic only after a call setup. A bidirectional communication channel present between the BTS and MS before the TCH traffic starts is called standalone DCCH, SDCCH. SADCCH, slow associated dedicated control channel, used for the registration, authentication and other requirements. Total 782 bits are sent as dedicated control channel data in 1S in case of slow associated standalone DCCH, SADCCH. 950 BPS can be sent as a control data slot in a traffic multi-frame. FACCH, fast associated control channel with TCH. When more than 782 bits are to be sent per second, then the TCH part of the data bus can be used. Then DCCH is called FACCH, fast associated control channel. BCCH, broadcast control channel. A BTS needs to broadcast the frequency and cell identity. A BTS needs to broadcast the information regarding frequencies and sequence options for hopping that can be assigned to the MSs in the cell to all the MSs. BCCH is used for this purpose. Enables an MS to get an available radio carrier frequency channel and transmit with different frequencies on different hops and synchronized with the BTS. The synchronization and frequency correction bus also use the BCCH. CCCH, common control channel. A BTS, when granting access to an MS so that MS can use either SDCCH or TCH, uses a channel called AGCH, access grant channel. After the access is granted, the call setup or call forwarding can take place. The control channel used for such purposes is called a CCCH. When call setup requirements are transmitted from the MS, CCCH is called RACH, random access channel. RACH. Data burst format during 577 µS in place of the H user data, S TR, S user data and T sequence. A 145-bit sequence is modified as 8 H bits, 41 synchronization bits, 36 bits user data and 3 T bits, total 88 bits. The guard space-time intervals are now equal to 68.25 into 3.692/2 equal to 126 µS before H and after T bits. PCH, paging channel. When call forwarding information transmits from the BTS, the CCCH is called PCH. Control multi-frames. A control multi-frame, 51 data frames. A control multi-frame transmits in 51 into 4.615 ms equal to 235.4 ms. A traffic multi-frame transmits in 120 ms. Superframe. After formatting, a superframe can have 51 traffic multi-frames of 120 ms each or 26 control multi-frames of 235.4 ms each. A superframe therefore transmits in 26 into 235.4 ms or 51 into 120 ms, both equal 6.12 s. Hyperframe consists of 2048 superframes. Transmits in 2048 into 6.12 s equal to 12,533.76 s equal to 3.5 hours. Sequence numbers s equal to 0 to 2048 into 26 into 51. 1 slots in a hyperframe is assigned to each 4.615 ms data frame. S encrypted along with the data so that after decryption, the original frame number can be recovered for sequential arrangement of data. Since the frames sequentially transmitted through the 8 TDMA time slots, the S also helps in identifying the original time slot of a given data burst. Handover. Handoff from one to another neighboring cell is defined as a mechanism to hand over the control of a mobile device to the neighboring cell. Process of transferring a call or data transfer in progress from one channel to another. The core network performs handovers at various levels of the system architecture, may hand over the call to another network altogether. Main reasons for handover in cellular networks. If the mobile device moves out of the range of one cell base station and a different base station can provide it with a stronger signal. If all channels of one base station are busy, then a nearby base station can provide service to the device. Handover process. Important one in any cellular network. Must be completed efficiently and without inconvenience to the user. Different networks use different types of handover techniques. Figure shows units of RSS and NSS performing handovers. Two main types of handover. Hard handover, GSM systems. Soft handover, CDMA systems. Hard handover. Existing radio link must be dropped for a small period of time, then taken over by another base station. A call in progress redirected not only from a base station to another base station, but also from its current transmit-receive frequency pair to another frequency pair. An ongoing call cannot exchange data or voice for this duration. Break in call transmission, call drop or call cutoff in hard handover. Handover takes place in a few ms, at best in 60 ms. Interruption is hardly discernible by the user. Handover to another cell is required when the signal strength is low and error rate is high. GSM systems perform hard handovers. Soft handover. 3G CDMA systems have soft handover. Mobile station at the boundary of two adjacent cells does not suffer call drops due to handover in the boundary region. Gives seamless connectivity to a mobile station. Soft handover does not require breaking of the radio link for cell-to-cell transfer of a call. A mobile device can be simultaneously connected to several base stations. Inter-cell handover. Measurement continuously performed at the RRM, Radio Resource Management, sublayers in the mobile station BTS and BSC. The RRM is also responsible for handover management. When the signal strength goes weak due to several reasons, for example, the mobile moving away from the cell in which it is presently localized to the boundary region of another cell, there is handover from a cell to another. This process is called inter-cell handover. Inter-MSC handover. Handover also takes place for load balancing when the traffic from the cells and BSC is high. An ongoing call, which is being handled by a cell, may be handed over to another MSC. Since the two MSCs are interfaced through PCM, the handover is performed over a wired line. Inter-BSC handover. Handover for load balancing when the traffic from the cells and BTS is high, the BSCs connect to an MSC. A call which is ongoing in a cell through a BTS may be handed over to another BSC connected to the same MSC. Since the BSCs connect to the MSC interfaces by PCM, the handover is over a wired line. Inter-BSC, inter-MSC handover. For load balancing when the traffic from the cells and BTSs as well as BSCs is high. Intra-cell handover. Due to interference at certain frequencies, the signal quality is poor. The BSC can hand over the call to another frequency of the cell in such cases. Inter-cell intra-BSC handover. When an MS moves to a neighboring cell and suffers poor signal quality, the BSC can hand over the call to a different BTS channel of the same BSC. Inter-cell Intra-MSC handover. The RRM sublayer transmits a signal report from MSI to BTSI and from BTSI to BSEI. In case a handover is necessary, BSEI signals the handover requirement to MSCI. MSCI signals the handover requirement to another BSCJ, and BSCJ allocates radio resources and transmits the activated channel to another BTSK. BTSK sends acknowledgement of the channel to BSCJ, and BSCJ acknowledges the handover request grant via message to MSCI. MSCI transmits handover command to BSCI, BSCI to BTSI, and BTSI to the MSCI's RRM layer. The RRM directs the MS radio interface to operate at another channel linked to BTSK. Handoff handover processes. New handover methods have also evolved and are used in addition to the older technique. 3G standards and technology makes it possible for several mobile phones to use the same channel and for neighboring cells to use the same frequency bands. International Mobile Telecommunications 2000 IMT 2000. 3G wireless communication standard defined by the recommendations of the International Telecommunication Union ITU. Below 3G, data rates lower than 153.6 kbps. 3G technologies, high quality of service and high data rate support for multimedia, audio, pictures, text and video transfer. 3G technologies covered in IMT 2000 global standards. Figure shows the 3G technologies covered in IMT 2000 global standards. DECT, Digital Cordless Telecommunication. UMTS, Universal Mobile Telecommunication System, standardizes mobile and transceiver station equipment, call setup session, security system, and radio access technologies. CDMA 2000 standards. Security in GSM services. A wireless radio-based network system, GSM, is quite sensitive to the unauthorized use of resources, designed to protect subscriber privacy. Secure network against misuse of resources by unregistered users. To control access to the network by mobile station, MS is required to use a PIN before it can access the network through UM interface. Authentication. An AUC, Authentication Center for the operation and maintenance subsystem of the GSM network. The AUC first authenticates the subscriber mobile station, and only then does the MSC provide the switching service. This service enables the MS to switch to another terminal TE, which is also authenticated in case it is a mobile station. Authentication algorithm. Use a random number sent by the AUC during the connection setup and an authentication key which is already saved in the SIM. Authentication algorithm used differs for different mobile service providers. TMSI. Its public identity. TMSI is the identity granted on moving to a particular location. When a mobile station moves to a new location area, the VLR, Visitor Location Register, assigns a TMSI which is stored in the SIM of the mobile station. The identification of the subscriber during communication done not using the IMSI but the TMSI ensures anonymous call number identity transmission over the radio channels. Use of TMSI. Caller light identification provision is a supplementary service. The VLR assigned TMSI generates that ID. This protects the mobile station against eavesdropping from external sources. Encryption. The BTS and the mobile station perform ciphering before call initiation or before connecting for receiving a call. The mobile station uses a cipher encryption key for encryption. The cipher is a result of performing mathematical operations on the cipher key saved in the SIM and the cipher number received from the BTS when the call setup is initiated. the BTS transmits the cipher number before a call is set up or transmitted. Mathematical operations performed are in accordance with algorithms employed by mobile service providers. Only encrypted voice and data traffic and control channel data transmits to the BTS. This makes secured wireless communication between the mobile station and BTS. The encryption algorithm identical for all mobile service providers. This ensures compatibility of the BTS, BSC and MSC units made by different manufacturers. The BTS deciphers the voice and data channel by running a deciphering algorithm before communicating over the wired PCM pulse code modulation lines. Random numbers used in authentication and ciphering processes are known as challenge to the mobile station to generate the responses of the algorithms. If these results are correct, only then do the BTS and other units grant access to the challenged mobile station. UMTS, Universal Mobile Telecommunication System, supports both 3GPP, 3G Partnership Project, and 3GPP2. Transmitter communicates at data rates of 100 kbps to 2 Mbps, combines CDMA for bandwidth efficiency and GSM for compatibility, supports several technologies for transmission and gives a framework for security and management functions. DS, Direct Sequence CDMA, supports a 3.84 Mbps chipping rate. WCDMA, another popular standard for mobile communication, deploys variable spread factors and uses asynchronous CDMA. WCDMA communication was introduced in 2000. Properties of WCDMA. Frequency spectrum: 1.920 to 1.980 GHz reverse, 2.110 to 2.170 GHz for forward. Each uses 5 MHz bandwidth. Forward link from BTS to MS and reverse link from MS to BTS. WCDMA FDD. WCDMA access is either FDD or TDD, time division dupling. WCDMA FDD, also referred to as UTRA FDD, Universal or sometimes UMTS, Terrestrial Radio Access Frequency Division Duplicate. FDD separates reverse link called uplink in GSM and forward link called downlink in GSM frequencies. Asynchronous CDMA system. Direct Access CDMA, DSCDMA, supports fast power control messages at 1.5 kbps closed loop control. IS-95 uses 0.8 kbps open loop control. Frame duration in WCDMA 10 ms, 15 separate time slots of 0.666 ms for reverse and forward links for the periodic functions not related to user data burst. Variable multi-rate transmission of signals by spread factor control. Supports data rates of 2 Mbps or higher for short distances and 384 kbps for long distances. Modulation type used in QPSK for both reverse and forward link frequencies. Timing synchronization of base stations does not follow GPS system timings. The common channels are control, paging, broadcast and shared channels, also a common channel for traffic. There are 3 dedicated channels to the MSS for uplink. Dedicated Physical Control Channel DPCCH, Dedicated Physical Data Channel DPDCH, Dedicated Physical Channel DPCH. The channel code and structure different for the uplink DPCCH and for the downlink DPDCH channel. Power control. WCDMA reverse link, mobile terminal uplink, transmits pilot symbols which are multiplexed with rate information as well as power control messages. Rate information facilities coherent detection. Signal code used when transmitting small data rate signals multiplexed in time-space and multiple codes are used when transmitting large data rate signals multiplexed in code space. Types of physical channels. Special distinct waveforms only. Each pair of spreading and scrambling codes defines the remaining physical channels. Protocol layers in the WCDMA uplink terminal MS and downlink equipment BTS. Physical layer. Physical layer is UU radio interface. Supports asynchronous transmission. Can also support synchronous transmission. Radio layer. Functions of radio layer. FDD and asynchronous or synchronous. Dedicated physical channel. Compressed mode. Bursting and 10 ms 15 slots framing. Power control. Synchronizing the MSs and MS path delay, correction, identification, primary and secondary synchronizing codes. Identification of scrambling code. 3.84 M chips, chipping, spreading and scrambling. Channelization, OVSF and scrambler, S2 or long 38,400 gold coding. Transport channel combining data interleaving and encryption. Measurements and soft handover. QPSK modulation and transmission. QPSK demodulation and reception. Data link layer MAC. Controls the flow of packets to and from the network layer. Ciphering function. Sends and receives data from control and user plane service access points at the radio link control RLC layer and sends it to the physical layer. Network layer above the RLCs. Provides access to multiple services such as BMC, Broadcast and Multicast Control Protocol for the user applications. PDCP, Packet Data Convergence Protocol for the user applications. GMM, GPRS Mobility Management. CC, Call Connection Control. Mobility Management. SM, Session Management. SS, Supplementary Service. SMS, Short Message Service. Key features of WCDMA processing units are user plane. Two sublayer protocols for user plane are PDCP and BMC. These are controlled by RRC, Radio Rescue Control, at network layer and are linked to RLC, Radio Link Control, at data link layer through a separate service access point. RLC performs transparent data transfer. Control plane. The sublayers in control plane are GMM, CC, SM, SS and SMS. These layers are linked to RRC, dedicated and common channels. Data link layer MAC protocols between MS and BTS support two types of channels, dedicated channels and common channels. Short and long data packets. Random access bursts are transmitted in 10 ms slots at fixed rates by a control mechanism, and slotted Aloha protocol is used for access. Short data packets directly appended to the random access bursts in common, not dedicated, channel packet transmission. Longer packets are transmitted by dedicated channels at variable power, controlled by a power control message appended to the user symbols. Variable rates by WCDMA processing units. Some types data need fast transmission rates and some slow. Variable rates are required in different types of services to form system. Orthogonal coding for channelization is asymmetrical in uplink and downlink. WCDMA employs a constant chipping rate for spreading but variable spread factors called OVSF, orthogonal variable spreading factors. Variable spreading factor. WCDMA also uses variable spreading codes but ones that are different from the Walsh code. Use of variable spread factor controls the signal with multiple data rates. The code length used per symbol is 4 when the downlink user symbol data rate needed is 1.92 Mbps. 512 when the data rate needed is 15 kbps. Spreading codes of different lengths thus used and orthogonality of the codes is maintained. The source MS and channel for these symbols when using orthogonal code spreading then gets uniquely identified on despreading at the receiver. Spread factor control controls the user data rate. When spread factor is equal to 4, user data rate becomes 1/4 of the rate corresponding to spread factor is equal to 1. OVSF codes support both orthogonality as well as variable data rates for a physical channel. Uplink OVSF does not separate the users due to different delays expected from the near and far terminals MSs. Variable rates in reverse channels. Uses gold and S2 codes. Chipping rates for these codes are 38,400 and 256 chips respectively. Gold codes used for the MS user symbols. S2 codes identify the user at the receiver. Compatibility with CDMA1, CDMA 2000 systems. WCDMA systems can be made compatible with CDMA1 and CDMA 2000 systems. Use of synchronous base stations. Employing multi-carrier mode with a chipping rate of 3.6864 M chips, which is an integral multiple of the IS-95 chipping rate of 1.2288 M chips. Adding a CDMA pilot to the direct spread mode data. Conclusion. In this chapter, we have covered the following in detail. GSM architecture and operations. Radio interfaces of GSM. Handover. Security. General Packet Radio Service GPRS. CDMA systems. WCDMA. IMT 2000. UMTS.